of the alveoli. Okay, so inspiration, and expiration. So now we're at the second phase, which is external respiration. So don't get that confused with expiration. Okay? External
I'm doing chemistry all over.
respiration, which is gas exchange between the alveoli and the pulmonary capillaries. Remember, oxygen is moving into the capillaries and carbon dioxide is moving into the alveoli. Okay, so that exchange, you guys remember the diagram I drew of the respiratory membrane? Remember what the respiratory membrane is made up of?
Simple squamous, the loose regular, and
So a
squamous.
sandwich of simple squamous epithelia. This is our alveolus with air. And then we had our pulmonary capillary, which had at least one simple squamous epithelium. And a minimal amount of connective tissue in between. Okay. Primarily really just the basement membrane, but I've excited it just a little bit. So this structure, the sandwich of the two simple squamous epithelia, is known as the respiratory membrane. And that's the site of gas exchange. All right? So what's the process by which gas is exchanged? Diffusion. Okay? So we'll be looking at all the factors that affect diffusion: concentration, distance, concentration being pressure, temperature, though we don't really change the temperature in the lungs that much, but all those various things that we described in Bio 430 that affect diffusion. So we're going to look at pressure first, our concentration. And remember what atmospheric pressure was we described on Tuesday?
760 millimeters.
So at sea level,
Oh, 760.
And
26,
mercury
26.
millimeter.
760 millimeters of mercury. Right? Now that's all of air. Okay? And air is a mixture of gases. So this is air, atmospheric pressure. The most common gas in this mixture is nitrogen. Anybody scuba dive? All right, so you've studied this already. Okay. Nitrogen is an inert gas, meaning it's not chemically reactive. It doesn't need to give up or accept electrons. That's what we mean by an inert gas. And so it's not chemically active in our blood, even though it forms most of the gas that is in our blood because it absorbs into the bloodstream as well. It becomes a problem, however, if you are diving and remaining under for 1 atmosphere of pressure. So 1 atmosphere is 33 feet of water, all right? So within that, you're pretty good. You don't have to worry too much about how long you're in the water. When you go below that, the higher atmospheric pressure drives more nitrogen into your blood, more than the atmospheric pressure. And so that can cause conditions known as nitrogen narcosis, which your brain acts like it's under the influence of alcohol. But more commonly, if you come to the surface too rapidly, the gas can come out of solution and cause joint problems and additional physical problems, including pain. But on Earth, above the water, that's not typically a problem. It is one of our gas mixtures, and it's almost 80%, all right? So approximately 78 to 79% of the air is nitrogen. So about 20.9% of the air that we breathe is oxygen. This percentage, almost 21%, is going to stay the same no matter what elevation we go up and down, all right? So when atmospheric pressure is 760, then the amount of oxygen of that 760 is about 159, 158 point something, that we round up to 160 millimeters of mercury. Remember back when I was talking about that pan of mercury and the vacuum tube? And I said, when you think about the pressure of gas, sometimes it's easier for students to change that number to actual oxygen molecules. It's not accurate, but it makes it a little bit easier to think about, all right? So these were 760 molecules of various gases bouncing around in a measured cubic space. 160 of them would be oxygen, okay? Most of the rest would be nitrogen, and about 0.4% would be carbon dioxide. Now, if we go up to 8,000 feet, 9,000 feet, then our atmospheric pressure is going to drop. It may, depending on the elevation, it could drop to 720, all right, or 700 or less. The proportion that is oxygen is still going to remain the same. The number of oxygen molecules will drop, all right? So it may drop from 160, if we're at 8,000 feet, it's about 115 to 120 millimeters of pressure. So we drop the actual number of oxygen molecules along with everything else. We're farther away from the center of gravity, and therefore there's fewer molecules per cubic unit of space, but the percentage is still the same. It doesn't drop to 15% or 10%. All right, so that value is going to stay the same. So Dalton's law means that the total pressure, so our 760 millimeters, is made up of the sum of all the pressures of the gases in the mixture. Right, so we just take the pressures of those individual gases, add them together, or we can go in the reverse. If a gas is 50% of a mixture, its pressure is going to be 50% of the total pressure. All right, so it works either way. And that's how we can come up with this value of 160 millimeters of mercury. Now, when we look at it in the alveoli, it doesn't stay at 160. Why not? It drops to, so if atmospheric air is 160, this is called the PO2, by the way, the partial pressure. Okay, so the partial pressure of oxygen in air is 160. So the PO2 in the alveoli is equal to 104 millimeters of mercury. The reason for that is because when we breathe air out, we're adding, as we breathe air in, carbon dioxide is added to the alveoli, and that takes up some of the partial pressure. So you'll see over on the right-hand side of the table on page 54, the percentage of oxygen drops because there's a mixture, and the percentage of carbon dioxide goes up. Okay. So if we convert this to millimeters, look down at the bottom, millimeters of pressure just under the table. Carbon dioxide, well, stick with oxygen here first. Venous PO2, so remember this is pulmonary capillary, it's blood that's come from the right ventricle to the lung. So it's what we consider, even though it's coming from the pulmonary arteries into the capillaries, it's actually venous blood that came from the systemic venous system, all right? Then it went into the right atrium, to the right ventricle, got pumped out of the pulmonary arteries into the lungs, but still deoxygenated blood. It's what was systemic venous blood in the body, so it's deoxygenated. So its PO2 is going to be approximately 40 millimeters of mercury, which is what our systemic venous blood is. So you can see we have a really high gradient. So diffusion pressure is, we have greater number of oxygen molecules in the alveolus. And that's going to a fewer number in the capillary. So our drive is going to be for a greater amount of oxygen to diffuse into the bloodstream. Okay. Whereas for carbon dioxide, we measure our partial pressure of carbon dioxide in the capillary blood. It's approximately 45 millimeters of mercury. And after we breathe out, so after we expire, we breathe air out, the partial pressure of carbon dioxide in the alveolus is not nearly as high a gradient, and yet we still have a drive of carbon dioxide. One of the major reasons why we don't need as great a difference between carbon dioxide in the capillary blood and in the alveolus is because our respiratory membrane is more soluble. Carbon dioxide has a greater solubility than oxygen. And so it's more easily transported by diffusion between the lipid molecules of our membrane, and therefore we don't need to drive it with as high a pressure gradient. All right, so what are some factors then that would affect this, other than the concentration? You look on the next page. All right, so the thickness of the diffusion distance. There's a couple of things that can affect this. If we have pulmonary edema or pneumonia, and we end up getting additional fluid in the alveoli because of the pulmonary edema or pneumonia, that's going to increase diffusion distance. All right. So diffusion distance or the respiratory membrane thickness, not necessarily the thickness of the epithelium itself, because that's not going to get any thicker, but the overall thickness of the respiratory membrane. So as the diffusion distance goes up, it's going to take longer for the oxygen and the carbon dioxide to move back and forth. Right? We can increase the thickness with, let's add that over here, so fluid due to pneumonia or pulmonary edema. Connective tissue, so we have pulmonary fibrosis. So we have an increased amount of collagen in here. Remember what we said that did to compliance? It made it lower because it was harder to stretch the lungs out. All right. Cystic fibrosis adds additional mucus. So that kind of comes in here with the fluid, but it's not just water. Can affect that as well. Okay. So let's take a moment here. If we have an increased diffusion distance, okay, what's going to happen to the PO2 in our capillaries? It's leaving the lungs. It's going to be lower. All right, what's going to happen to the CO2?
It's going to go high.
It's going to be higher, all right, because it hasn't been able to diffuse out. So we're going to have blood coming back to the heart and being pumped out of into the aorta with lower CO2 and higher CO2. So we'll look at that on a little bit when we talk about on control of respiration and factors that cause you to take more shallow breaths or deeper breaths to change the rate of breathing when we have lecture on Tuesday. All right, then we have the surface exchange area. So this is the number. Let's say that we have another alveolus over here, it has a capillary. But then because of damage to the alveolar walls, the most common cause of which is emphysema, we lose alveolar walls. So now we have, instead of two smaller alveoli, we have a larger alveolus. So we've lost some of our surface area. We still have the same amount of oxygen in here, but we have not as much surface area. It's going to take longer for this oxygen to get to the blood vessel than if we had another blood vessel in there. All right, so another factor is the surface exchange.
Because the increase in surface area?
This would cause a decrease.
Yeah.
So diseases that cause loss of alveolar walls, such as emphysema. Now, notice the blockage of the alveoli. So a tumor that doesn't allow air to get in here, not only is it not allowing oxygen to get there for exchange, but eventually that will collapse, all right, and not be available. All right, so emphysema is a form of obstructive pulmonary disease. We talked about the fact that that would increase residual volume, decrease the forced expiratory volume in 1 second, because it also has narrowed airways. Blockage of airways is restrictive. So a bronchial tumor, or if we fill up these areas with fluid, we also have lost surface area. Okay? So if we have an alveolus that's completely filled with fluid, that entire alveolus is not going to be able for gas exchange. So it can also result in a decrease in surface area. All right, ventilation, perfusion, coupling. Ventilation is the movement of air. And you'll hear, if you go into respiratory therapy, you're going to be talking about ventilation, perfusion, coupling a lot. Ventilation is the movement of air in and out of the lungs. Perfusion is the flow of blood through the blood vessels. All right, so you can affect the ability of gas exchange to occur if we have a problem with ventilation. So if there's a blockage in the airway, if there's less oxygen in the air that you're breathing, okay? If there's partial paralysis or a collapsed lung, that's a ventilation problem. If there is a perfusion problem, we've got a problem with the cardiovascular system. Okay, so maybe the blood is flowing too slowly, it's too thick with viscosity, or blood pressure is really low, so it's flowing at a rate that's not picking up oxygen fast enough. Or maybe blood pressure is too high, so it's just going really fast through the pulmonary system. And it's like trying to jump on a canoe that's got an outboard motor on it. You can't just step into it because it's gone by the time you try to jump in, you'd miss it and end up in the river. Okay, so there's a proper flow rate for the blood to flow through. So along with this, we've already discussed this when we talked about metarterials and we talked about capillary flow. So remember, typically, let's say that we're running and my calf muscles, my gastrocnemius and soleus need more oxygen. What's going to happen to the flow to the capillary beds of those particular muscles compared, say, to my triceps brachii?
They're going to get big.
I'm going to get more blood flow, all right? Remember I said in the lungs, the opposite occurs? If I have, I still don't have a screen now. If I have a lack of oxygen, decreased, let's say I've got pulmonary edema here, all right? So the blood in the capillaries flowing by because of the increased diffusion distance is not getting sufficient oxygen, that capillary bed will shut down. Because I'm just wasting blood, sending it through an area that has inadequate ventilation. And the blood will be redirected to go through an area that has better oxygenation. Okay? So we talked about this a little bit when we were talking about capillary flow. So that's the ventilation perfusion coupling. It's the reverse, because the purpose here is to pick up oxygen, not to deliver oxygen. Yeah?
Can I ask a question about the obstructive and restrictive?
Uh-huh.
So I remember when you said obstructive, it was just like a big boulder. I guess you example like in a trachea. So does that just like stop air completely
It
coming in?
narrows,
And
it,
then-
well, it can. When that happens though, it then changes to restrictive. Because if we block the airway completely, then we lose all that volume of gas exchange. So we've lost, say, a whole lobe of air if we block the secondary bronchus of that particular lobe.
Mhm.
So think of it more of narrowing.
Okay.
It takes you time to climb over the boulder to get to the other side so you can continue through the tunnel.
But then restrictive is completely.
Restrictive is it blocks, it restricts the get, it's more down at this area. Rather than getting here,
Mhm.
this is no longer available.
Okay.
Here I had all these cool pictures of hemoglobin. Okay. Now I raise this side of the board. So now we have our oxygen into the capillary. So I'm going to just draw part of this in a larger capillary. So as oxygen is diffusing over, and this is can be a difficult concept sometimes to understand. We have a gas in air. Most people understand that. Your gas molecules in the air. It diffuses through, is soluble across the simple squamous epithelia, and now it's in the plasma of the blood. Okay? It's dissolved with amongst the water molecules. As such, it is still a gas. Okay? Mixed up with the water molecules, the water and gas molecules mixed up together, it still exerts a gas pressure. So when we talk about the PO2 of our arterial blood being 104, because by the time it goes through the whole series of alveoli, it's going to equilibrate with the lung PO2. So as it goes back to the heart, it's going to be equal to the PO2 of the air. And what that means, again, we're back to using numbers instead of pressures. We have 104 molecules of oxygen in the same volume as we had in the air. And these are gas molecules. So they're bumping around. In actuality, they're exerting the same pressure as they bump against other water molecules. They're the same concentration, dissolved in the fluid. So when we talk about PO2 of blood, it's free gas molecules. As soon as it binds to hemoglobin, it no longer exerts a gas pressure. All right, so we have two measurements to determine how much oxygen is in the blood. We have the PO2, and then we have the percent bound to hemoglobin. So hemoglobin is in our red blood cells. And as we have oxygen moving into the blood, as it moves into the blood and increases its concentration, this will move into, across the red blood cell membrane, and will bind to one of the iron atoms, ions, of hemoglobin. Once it moves in, notice that creates space in our gas pressure for another oxygen molecule to move in. Does that make sense? Because the PO2, the oxygen dissolved in the plasma, is never going to be higher than what we have in the alveoli. So we can transport more oxygen by taking this oxygen and binding it to the iron. We move those 4 into the blood cell, we can move another 4 into the plasma. If all you had was plasma PO2, that is insufficient to keep you alive. Right? If you had no red blood cells at all, you wouldn't be able to transport enough oxygen dissolved in the plasma for the needs of your body, your blood cells. So we need to have the hemoglobin, all right? We need to have an adequate amount. So as you can see on the lecture notes, the molecules bind. The first one to bind has a lower affinity. Once that binds, the second one has a higher affinity, and the third one, the other way around. This one has it binds more easily, so it has a lower affinity. In other words, this fourth oxygen is going to come off because it binds, it's going to have an easier time coming off as we drop the PO2, all right? So it gets easier and easier to bind, and so then when it comes off, the reverse occurs as we drop our oxygen components. So when we saturate this, we're talking about all iron atoms have oxygen bound to them. When we're not going to have 100% saturated hemoglobin if we don't have a maximum amount of oxygen dissolved in the plasma. So the drive for oxygen to move into the hemoglobin, into the red blood cell, is a high PO2. That's what keeps the oxygen bound to the hemoglobin. Okay? So on the reverse, when we look at oxygen leaving the hemoglobin, then we need to start removing the oxygen in the plasma. We need to start dropping the PO2 in the plasma for the oxygen to come off. And that occurs in internal respiration at the tissues. So the next diagram, when I can get my slides to work, I'll come back and go through the material that's on the bottom of page 58. The next diagram, the next page shows a series of diagrams called the oxygen dissociation curve. So I'm going to erase the far side. Anybody need pictures of that? Can I post that?
Can you explain, just make sure, if you have movement of oxygen into the hemoglobin, it causes a high PO2,
Yes.
but if you remove...
Well, wait. It requires a higher PO2.
Okay.
So let's say, I'll go over that again because it's essential. So we have our, let's do normal and then let's do high altitude. When we have oxygen in our alveolus with a PO2 of 104, and we have our blood coming through the capillaries, this has a PO2 at first of 40, right? Because it's coming in from the heart. And so we're going to have oxygen driven because of the concentration gradient. Oxygen from the alveoli is going to move into the plasma. Now that will drop this PO2, but remember this isn't static. We just take a breath and we refresh it back to 104, okay? This is not going to just come by one alveolus and then go out the lung. It's going to go by thousands of alveoli. And so, in essence, we have a constant, relatively constant PO2 of 104 in the alveoli. And as this flows slowly by thousands of alveoli, this is gradually going to increase until the PO2 of the plasma is 104. It doesn't do it all at once, all right? While that is happening, as this gradually increases and more oxygen is dissolved in the plasma, some of that oxygen will cross the plasma membrane of the red blood cell. When it does so, because this is still 104, another oxygen will take its place, and even more as we gradually move through the lungs. So this is gradually getting increasing oxygen. That oxygen comes in and